Good day and welcome to the part 1 of my video lectures regarding the formula derivation of internal inductance of a conductor. The objectives of this lecture are: number 1, to learn the philosophies in deriving the internal inductance, to learn the physics of derivation, and to learn the few mathematical methods like differential and integral calculus. The inductance formula of one conductor in a two-wire single-phase transmission line is L1 is equal to 2 times 10 to the negative 7 logarithm D over R1 prime in Henry per meter, where L1 is the inductance of conductor per unit length in Henry per meter. D is the distance between conductors in meter, and R is the radius of conductor in meter. This is the formula we are going to derive. But before we can arrive on this formula, we need to derive first the formula of internal and external inductance of a conductor. Now suppose a conductor has current flowing in it in this direction. What will happen is that it will generate a magnetic fields or magnetic flux inside and outside of the conductor, and the directions of this field will be known by using right-hand rule. The thumb points in the direction of the current flow, while the fingers will curl in the directions of the magnetic fields. So there is an invisible magnetic fields generated when current is flowing in a conductor, just like a permanent magnet with inherent magnetic fields present. To start with our derivation, we will first assume a conductor with 1 meter long and with radius r. This conductor has current flowing in it. That's why it generates a magnetic field H, internal and external of the conductor. Since we are deriving first the internal inductance, we assume that the internal magnetic fields is in circular path, which is the red dashed lines. Since it is circular, we will assign its radius as x in meter. We will be thankful with Sir Andre Ampere because of his discovery regarding the presence of magnetic fields in a conductor when current flowing in it. This magnetic field or magnetic flux phenomenon was discovered by Sir Andre Ampere, a French physicist and mathematician, on 1819, by which he called as electrodynamics. This is also called as the new law of nature, which he named after him as Ampere's law. This law states that when current is flowing in the conductor, the magnetic field or magnetic flux will be generated and circulates around the conductor. It is stated also that a magnetomotive force MMF around any closed path is equal to the net currents in amperes enclosed by the path, which is also equal to the surface integral of the magnetic field or flux intensity Hx around the circular path. Mathematically, MMF is equal to Ix enclosed is also equal to the surface integral of Hx times ds, where s is the distance along the circular path in meter. Ix is the current enclosed. Hx is the magnetic field or magnetic flux intensity or strength in ampere turn per meter. And x is the radius of the circular internal magnetic fields also in meter. Therefore, Ix enclosed is equal to the surface integral of Hx times ds. From the previous slide, we write that Ix enclosed is equal to the surface integral of Hx times ds, where s is the distance along the circular path in meter. The integral of ds is simply 2 pi x, which is also the circumference of the circle, while Hx remains constant because it moves at all points along the circular path at distance x from the center of the circle. After integration, the equation will become Hx times 2 pi x is equal to Ix. And equating Hx is equal to Ix over 2 pi x in ampere turn per meter. Since we are considering only the internal magnetic fields, in the conductor, we will notice that current Ix is a small part of the whole current I. Therefore, current Ix is a proportion of whole current I with respect to its own area. We can say that the whole current I is proportional to the area of the whole conductor with radius r, while the small current Ix is proportional to the small part of the conductor with radius x. Mathematically, I over pi r squared is equal to Ix over pi x squared. And solving for Ix, it is equal to pi x squared over pi r squared times I. Substituting the value of Ix to the formula of Hx, we get Hx is equal to pi x squared over pi r squared times I over 2 pi x. Therefore, Hx is equal to xi over 2 pi r squared in ampere turn per meter. We already derived the magnetic field or flux intensity Sx in the previous slides. As we will see in this figure, this Sx are circumferential surface 1 meter in length. The next thing we will determine is the density of the magnetic flux, and this is the number of magnetic flux in Weber in a certain area in a square meter. We will assume that the thickness of this circumferential surface is dx. The small area dA that we are going to consider is only the one slice of this circumferential surface with thickness dx and 1 meter in length. So the magnetic density we will be going to determine is dBx in Weber per square meter. Based on the study by physicists and scientists, the number or the amount of magnetic flux to be produced is dependent on the magnetic properties of the material. In our case, is a conductor. The magnetic properties of the material was called as permeability U of the material or conductor. In that principle, we can say that the magnetic flux density Bx has mathematical relation with magnetic flux intensity Hx and with the permeability U of the conductor. Therefore, the number of magnetic flux density Bx will depend on the strength of magnetic flux intensity Hx and with the properties of the material, which we called as the permeability mu of the conductor. Mathematically, the relation will be written as Bx is equal to mu times Hx. The fact that the actual transmission lines are exposed to the environment with the presence of air, and since air is also a matter or material, it has also permeability like the conductor. And this is called as the permeability of free space mu naught. Since we have two kinds of permeability, permeability of conductor mu and permeability of free space mu naught, the ratio of this permeability will be called as relative permeability mu r. Mathematically, mu r is equal to mu over mu naught, where mu r is the relative permeability, mu is the permeability of conductor, and mu naught is the permeability of free space or air. Based also in the study, the relative permeability mu r of non-magnetic material like wood, plastic, glass, copper, and aluminum is equal to 1. Therefore, the permeability mu of the conductor will be equal to the permeability of free space. Since we already determined the magnetic flux intensity Sx as xi over 2 pi r squared and mu is equal to mu naught, substituting Sx and mu to this formula, therefore Bx is equal to mu naught xi over 2 pi r squared in Weber per square meter. We already determined the magnetic flux density Bx in terms of magnetic flux intensity Hx and permeability mu. The next thing we will determine is the number of magnetic flux using the formula of magnetic flux density Bx in terms of the number of magnetic flux per area A. Therefore, B is equal to number of flux over area A. What we are going to determine next is the number of magnetic flux. We already have magnetic flux density Vx, but we need to determine first the area A, wherein the number of magnetic flux will be computed. In this figure, the red dashed lines is the small slice of the circular magnetic fields, and this is the area to be considered where the number of magnetic flux will be determined. It has a thickness Tx and has a length of 1 meter. Since it is a very small area, in calculus it will be considered as infinitesimal area A, and this will be called as dA. To get dA, it is simply the width dx multiplied by length of 1 meter. So dA is equal to dx times 1 meter. Therefore, dA is equal to dx in square meter. We have infinitesimal area dA, which is dx times 1 meter. It is also in this area that Bx has already determined, and it is also the area where to determine the number of magnetic flux. Since it is a very small area, it is right to say that Bx is dBx and flux x is d flux x. Therefore, the formula will become dBx is equal to d flux x over dA. Equating d flux x is equal to dBx times dA. Substituting the value of dBx and dA in the formula, therefore d flux x is equal to mu naught xi over 2 pi r square times dx. If you will notice, we started from Ampere's law to get Hx, then from Hx we get Bx, then from Bx we get d flux x. What we are going to achieve is the internal inductance of the conductor. And based on electromagnetic principle, the inductance L is equal to the flux linkage X divided by the current I, where the flux linkage X is the linking of magnetic flux within the circuit. So we need to determine first the flux linkage X before we can determine the inductance L. Since we are going to figure out the flux that links the circuit, we will remember that the internal magnetic flux we had assumed as a radius of x from the center of the conductor, and the area of this circle is pi x squared. Therefore, this pi x squared was enclosed by the magnetic flux x, and it is the area that links by the flux. But this pi x squared is a proportional part only of pi r squared. Mathematically, pi x squared over pi r squared. So the part of the conductor that links by the internal magnetic flux will be the ratio of the two areas, pi x squared and pi r squared. Therefore, the flux linkage X of the circuit is pi x squared over pi r squared times d flux x. Substituting the magnetic flux d flux x to this formula, therefore the final flux linkage of the circuit is d flux linkage x is equal to pi x squared over pi r squared times mu naught xi over 2 pi r squared dx. Therefore, d flux linkage x is equal to mu naught ix cubed over 2 pi r to the fourth dx. What we determine is only the infinitesimal flux linkage, d flux linkage x of the area dA. But what we need to determine is the total internal flux linkage of the circular strip. We will notice that the equation of flux linkage, d flux linkage x, is a function of x. As determined already in previous slide, the equation of flux linkage is mu naught I x cubed over 2 pi r to the fourth dx, and it appears as a function of x. This is only the equation of flux linkages of one slice of this circular strip. In the earlier civilization, this type of equation, where its graph or figure is an irregular shape, is difficult to calculate each area under its curve. So we must be thankful with physicists, philosopher, and mathematician like Isaac Newton and Leibniz, who have devised a mathematical method that will calculate the area of irregular figures or graph like parabola, etc. This is called as area of a function or area under a curve by using integral calculus. So to determine the total internal flux linkage or the area of a function, we should integrate the flux linkage d flux linkage x from the center to the tip of the conductor, which is from 0 to r. The total flux linkage of the conductor is equal to the integral from 0 to r of mu naught I x cubed over 2 pi r to the 4th dx. And moving the constant term outside the integral sign, flux linkage internal is equal to mu naught I over 2 pi r to the 4th integral from 0 to r of x cubed dx. But before we will proceed with the integration of this equation, I would like to show you first the fundamental theorem of integral calculus. This is the fundamental theorem of integral calculus. We have an approximate value where the area under a curve will be divided into rectangles where its width and length was known, and then adding the area of rectangles by using this formula. And we have also an exact value using integral calculus. Since the exact value theorem is usually used today, we will focus only on this theorem, wherein in this theorem it has a certain point under a curve with width of dx under a curve. The formula is a is equal to integral from a to b f of x dx. But to get the area under a curve, you need to integrate the equation of a function and then evaluate the result of integration from its range by using this formula, where f is the integral of a function. In this equation, the integrand is x cubed. So the integral of a function x cubed is equal to x to the 4th over 4. And using the area formula, evaluate x from 0 to r. Therefore, the internal flux linkage is equal to mu naught I over 8 pi. But the value of permeability of free space is mu naught is equal to 4 pi times 10 to the negative 7. Substituting that value, we get flux linkage internal is equal to 4 pi times 10 to the negative 7 I over 8 pi. Therefore, the internal flux linkage is I over 2 times 10 to negative 7 in Weber turn per meter. So from the formula of inductance, substitute the value of internal flux linkage. Therefore, internal inductance is equal to I over 2 over I times 10 to the negative 7. The current I will be cancelled, and therefore the internal inductance is equal to 1/2 times 10 to the negative 7 in Henry per meter. It is interesting to note that the internal inductance of the conductor is independent on the conductor radius. That's the end of my lecture regarding the derivation of internal inductance. In my next video, part 2, I will discuss the derivation of external inductance. Thank you.